Hello, my name is John Gabriel, and this is the new Calculus channel. So in this part of the series called What You Had to Know But Your Ignorant Teachers Could Not Tell You, I'm going to attempt to cover all the requirements, not axioms or postulates, and I'm going to do it slowly, so it might take a little longer than it usually does. And if I don't finish, then I'll stop and continue in another video. So bear with me. Now, let's begin with the very first notion, which is the point. Okay. So what is the point exactly? Well, it's just a concept of location or place. In an empty universe, it cannot be defined, okay, except possibly as two states. So let's say we're in an empty universe over here, right? And we're over here where you see the point. So what does location mean? We're either here or not here, somewhere else, right? And it doesn't matter whether it's a plane or a 3D universe, right? Okay, so from this particular notion or of concept, here or not here, we can gradually build up and refine the definition of location. And that's how the ancient Greeks did it. So from this, a rudimentary motion can be defined. So for example, you could say, if you had another point, let's say another location in space, say over there, you can say that a motion can be, a rudimentary direction can be defined as towards or away, right? Towards or away, okay? And rather than invoke the notion of distance between these 2 points, we can use one of our physical senses. So to understand the toward direction. So toward direction means gradually getting closer to this point, right? And the away direction, meaning the object gets further away. And one way you can visualize this is that if you were getting close to the object, it gets bigger. And as you're getting away, it gets smaller. Now, notice that if we didn't have eyesight, we could use our hearing sense. So for example, if somebody is constantly talking and we're getting closer, it gets louder. As we're getting away, it gets fainter, etc. But notice that we don't actually need these physical notions to understand distance, because even people who are blind and deaf can acquire an understanding of distance. Okay? So now, what is a path? By the way, a path is basically described by the motion from one location to another. All right. So let's look at this. There are many paths between any two different locations, some with more directions and others with less directions. So let's say, for example, that we had this here and we wanted to, now let's see, how can we draw in here? Can we draw in here? I think we'd have to do it here. Okay. So we could go from here, oops, I need to just change that color. And we're not seeing it because it's not white, but I'll make it a white color. Well, I think you get the idea. You start at one path and you end up at the other, right? In many different ways you can do this. So I'm going to undo that. Back here again. Okay, so you can have many different paths between these 2 points. Watch this hand. See, I can go like that, or I can go out here and back to that point. So some with more directions and others with less directions. Any change in the direction alters the view of this object. So if I'm here and I'm looking at this object and I'm just going straight like that, the view is not going to change, okay? But if I turn this way, I'm not going to have the same view. And so we can see that more or less here are defined in terms of primitive counting. That is a one-to-one correspondence between the directions of each path without regard to the direction sense, right? So now at this time, we're ready to define the concept of straight line. And you can just get these paths out, these points out of the way, put them back here, okay? So what is the straight line, really? It's just defined as the path between 2 points in which the rudimentary direction towards or away remains the same, okay? So the directions of any path give rise to the primitive notion of length or distance, which is realized by asking the question how far or how near, etc. Any path with more directions than a different path is said to be longer, since each rudimentary direction is a motion from one point to the other. And since no path has less directions than the straight line, it follows immediately that the straight line is the shortest distance between any 2 points. So as you can see now, I've shown you how to reify the straight line. No problem. Don't need to believe in anything. There's no requirement for axioms or postulates or any of that nonsense. And similarly, we can extend or shorten a straight line, and the proof of this is very easy. Because to prove that any straight line can be extended, all one has to do is consider a random portion of a given straight line, right? So if we have a random short portion, we know that this is possible since a straight line is possible between any 2 given points, and we are done. A portion is realized by not completing the path, that is, fewer of the required directions, okay? This second requirement here is all that is needed to continue with the perfect derivation of number from nothing. So we could stop here without doing requirement 3, 4, and 5 and derive number. But I'm going to carry on with these because I want to show you how you can derive all the geometric objects, okay? The remaining requirements are needed to complete the formulation of Euclidean geometry, 3, 4, and 5. So let's continue. Now, if you have a circle, this here is also derived from the straight line. And how is it derived from the straight line? Let's see. Well, let me just turn this on. Okay. So if we just enable ourselves to draw on here. Oops. Okay, come on. Okay, so screen sketch. All right. So now we're going to draw on here. So it says here an origin path, and I've just called it that to differentiate it from any other path. In other words, it's special. Supposing we have a circle like this, okay? It's roughly a circle. Doesn't matter. And an origin path, in fact, I'm not even going to restrict it to a plane because I want an origin path to be in 3D. So I'm going to go back here and just choose a different color now. Choose black. So an origin path is any path that starts at a particular point, right, and ends up at the same point, this point here. Now, if we just stop there, that could be called a circle because the distance from all these points on the path are the same to the circle, right? They're all the same radius, right? So that's not enough to define a circle. So we'd have to say a circle is that shortest origin path from which the distances to a given point, the center, are all described by the same straight line, this radius, and another straight line. So a straight line, a diameter which goes through the center and ends up on the circle. Now you'll see that will only be true if this object is a circle, okay? So you need to think about that. Now using the circle, we can define any plane as that object which is overlaid or spanned by a circle of increasing radius. To avoid confusion with the sphere, we add the requirement that any of the circles must be spanned by the same straight line extended in any direction. And all the paths in a plane comprise what is called a surface. Now, we don't really need these for the rest of the requirements. I've just added in those two for good measure. The next thing we want to look at is the definition of an angle. Now, Euclid says that an angle is formed in a plane when two lines are at an inclination to each other, right? So in other words, where two straight lines meet. This says straight, but it's missing a T here. Never mind. In the diagram below, the angles are named 1, 2, 3, and 4. But now, remember, this isn't really enough to define an angle correctly, because if we move these around like that, we will certainly get a different angle. So if we redefine the definition, Now, in terms of this definition here, where we have the length of this blue line, which is known as an arc, and we compare it to the green line, then we can define an angle as this length to this length of the green line, right? In terms of unknown sizes or magnitudes, because we don't have numbers yet. So we define a ratio to be the comparison of two magnitudes, the magnitude of this, the length of this blue line and the green line. And we call the measure of angle 1 the ratio, which is defined as this blue arc to the radius. And so we can redefine the angle that way perfectly, so that it doesn't matter how we construct these two lines. They can be shorter or longer, but the angle will remain the same, okay? So it doesn't matter what we do here. This angle will always be the length of the arc to the radius. Now, it's very important to remember that Euclid wanted to define these based on what was previously defined. So he couldn't just jump ahead right away, okay? And now the next requirement was that all right angles are equal. And a lot of people say, well, why even say that all right angles are equal? Why not say that all 45-degree angles are equal? Well, there's a reason to this. First of all, let's just read here. Symmetry is the property or attribute of being made up of exactly the same paths, lines, or parts in general. Now, any diameter bisects a circle circumference into equal paths by symmetry. So if you had to have a circle like that and one diameter, then this part of the circumference will be exactly the same as this one by symmetry, right? And another diameter which further bisects each circumference so that we have 4 equal parts is called a perpendicular bisector. So here we've used this to define right angles, okay? Now, because Euclid hadn't done it in this order, he basically had to state that they're equal. Why? Let's see why. Euclid understood that an angle in a triangle can be changed by altering the distance of either side. So if we move this along, if we alter this distance here, both this angle and this angle will vary. Do you see that? They change, but the right angle remains the same. It doesn't matter how you vary these two, okay? Does that make sense? However, if we have another type of triangle, then if we vary the other angles, there's only one exception that does not change, and that is the right angle. See, if we do that, all the angles change if we vary this distance, right? The other angles change, right? And so coming back to the right angle, which is this one here, it doesn't matter how we vary these, okay? We can vary them any way we like, and the other angle will change, right? But it's not true of the right angle. The right angle will remain unchanged. It's the exception. So all right angles are equal, all right? Doesn't matter how you vary these, all right? This is the exception. So if you do that, then there's no right angle here. And if you vary any one of these, nothing is guaranteed to be constant, see? And one of the consequences of this kind of thinking is that, for example, this length here tells us a little bit about how great this particular angle here is. In other words, if this length is shorter than this length here, which I'm pointing to, then this angle must be greater than this angle, right? But that doesn't actually have any effect on the right angle, okay? Do you see? It doesn't matter whether one length is shorter or longer, the right angle remains the same. So that is the reason why Euclid stated that all right angles are equal, okay? But if he had done it this way, which I showed you here, and he said, let's go back to this one. I kind of lost my track here. Okay, if you defined it this way, by saying that any diameter bisects a circle circumference into equal paths, right? Then another diameter which further bisects each circumference half, so to speak, and I didn't use the word half because they're symmetrical, into equal parts is called a perpendicular bisector. In such a case, both diameters are perpendicular to each other. So I suggest that what you do is stop the video and read this carefully so that you can make sure that you understand it in your own minds. And so in many of his further proofs, he says the angles are formed when two diameters are perpendicular to each other and the angles are subtended on equal arcs. Okay, so this is very important that they're subtended on equal arcs, because remember I told you something about distances here earlier on? Okay, I said that if this distance, oh, I didn't mean to do that. Actually, I mean to look at this one. If the distances are greater, then the angle is greater, right? So, for example, if we do that, if this distance is greater than this distance, then this angle here will be greater than this angle and also this angle, because this distance is greater than these two lines. But it varies if it's not in a circle, right? So if the triangle is concentric, that means it lies on a circle circumference with one of the vertices at the origin, then we can easily just say that now I'm losing my touch out. We can easily just say that it's going to be the same if they're subtended on the same arc, okay? So coming back to this, all are equal because the angles are subtended on equal arcs, okay? But if you don't have a circle, then that's the reason why you have to say all right angles are equal. And while I'm saying that, you can have a laugh at the hilarious opinions of professors in the big stupid. So for example, this one here at this particular site, pit.edu, says that whenever we create a right angle by erecting perpendiculars, the angles so created are always the same. And then he says, sameness here means that we manipulate angles by sliding them over the page. Well, Euclid did no such thing, okay? And he says it may seem that a postulate like this is superfluous. It's not superfluous, but not because of the reasons that he states, okay? He states that could it really fail? Yes, no, it can never really fail. And he says the size of a right angle is the arc of a circle is subtends divided by the size of a radius in a neighborhood close to the point. So this is entirely garbage. He doesn't know what he's talking about. And he says, nonetheless, the equality of right angles still needs to be asserted. No, it doesn't. It is stated very clearly because if a right angle is defined in the way that I showed you using a circle, right? Using a circle, and coming back to this point, using this method here, we don't have to make any assertions because we're simply using symmetry to show how the circle is divided into halves and quarters, right? And we don't call them halves and quarters at this time. We just call those portions equal because they're equal arcs or sub-arcs, right? All right, so at this point, I would suggest you stop the video and just carefully understand these requirements up till the right angle. Now, before we can continue, we have to look at how to derive parallel lines. And once we've got all these four requirements in place, we're ready to define parallel lines. So a straight line that meets a circle so that the arcs between the line and the diameter, these arcs, the red arcs, are the same on both ends of the diameter, then this line here, this blue line, is parallel to this diameter, okay? And the diameter is parallel to the straight line. Why? Because these arcs are equal, okay? So we've defined parallel lines to be the lines that are subtended on the same equal arcs given any diameter. Now, before we can prove the last and the fifth requirement, not the postulate as those orangutan morons in the mainstream or the Church of Academia think, we need to have some preliminaries. So we first define a transversal as a straight line which meets two other straight lines. And in this case, I'm going to just assume that they are parallel because I want to discuss co-interior angles and alternate angles. So now, when that happens, and we have angles like this, these angles here, on the inside, on the same side of the transversal and the same side of the parallel lines, we call them co-interior. And if they lie on the opposite sides of the transversal, they're alternate. And now, of course, the next thing we can do, the final thing we have to do, is show that if we have a triangle between parallel lines, that the angles in a triangle are always two right angles. And this is easy to prove. So for example, if we have co-interior angles, we can note that this angle and this particular angle here lie on this straight line. Therefore, they must be two right angles from the previous definition, okay? Where we defined right angles. We said that if we have diameter and we divide a circle and we divide it by a diameter, then we have two equal symmetrical paths, and we further divide those paths, then we have what's called a right angle, right? So coming back here again, we use that particular fact to show that if we have this angle here, the sum of this angle and this angle will create two right angles, and hence it must be the case that this angle plus this angle are always two right angles, because this angle here is equal to this alternate angle on this side here, okay? So now we've actually shown that alternate angles and co-interior angles have a sum of two right angles. And I remember Euclid measured all angles in terms of right angles. And of course, a straight line consists of two right angles, because two angles that are supplementary must have a sum of two right angles. And there's nothing to believe there. Nothing is required on faith. It has been shown by the fact that we divide a circle with a diameter and then again with another diameter, so that the paths by symmetry are equal into four paths, okay? And so finally, we show also that these the sum of these angles here are two right angles, and we can do it now because we know that this is a straight line and there are two right angles. This is the only one that's different. Therefore, there must also be two right angles. And now finally, we can go to the fifth requirement. Now, the fifth requirement is most commonly not understood because it's claimed to be a postulate. It's not a postulate. It's derived from all the previous requirements. What it says is that it doesn't matter how a transversal falls on two lines, these two lines here, okay? It doesn't matter how it falls on those two lines. The sum of the angles on either side of the transversal are constant. See, so if I move this along, look down here, 168 and 191, it doesn't matter what I do, they're going to remain the same, right? It's going to remain the same. That's what the fifth postulate says. And it says that if these two lines meet like that, then this sum here will be less than two right angles, and consequently this sum here will always be greater than two right angles, okay? So there's that other part which Euclid didn't bother to mention because it was obvious, and the morons in mainstream academia today are too stupid to realize it. Now, although Heath did a pretty good job in translating the elements, he really made a little bit of a mess where it comes to these, because the Greek word here is atimata, which means requirements or claims. They're not postulates or axioms. In fact, the word postulate or axiom doesn't appear anywhere in the book, in any of the books, the 13 books of Euclid's Elements. So he didn't understand, and nobody before me understood these facts. I was the first to understand these facts, and I was the first to prove that you can derive all these requirements from nothing, building from the previous ones that you've derived. Okay, so nothing here has to be taken on faith. And Heath was wrong also, and many others were wrong in terms of understanding the common notions also. Looking back here at some of these opinions, it says, while this postulate asserts the fourth postulate asserts that the essential truth at a right angle is determinate magnitude. Basically, he says that Euclid preferred to assert as a postulate. He didn't. Euclid understood that all right angles are equal from the proof that I showed you earlier on, where you divide the circle with a diameter and then again with another diameter so that the paths are equal by symmetry, okay? And those were perpendiculars. So you can look at many other opinions, and they're all wrong, by the way. So I hope I've given you a good understanding now into the axioms, not the axioms, into the requirements and claims. See, even I have to watch out because I can sometimes call them that by habit, but they're not axioms. There are no axioms or postulates in mathematics. And so this is a very important presentation, probably one of the most important out of all the other ones, similar ones that I've done. And I'm going to post a link to this applet so that you can play around with it. And also, I would recommend that you download this video, because the mainstream priests will do their best to tell you that it's not right and that what I'm telling you is incorrect, but this is the truth, and you're hearing it from me. I am the discoverer of the first and only rigorous formulation of calculus in human history. So I'd admonish you to take what I'm telling you seriously and study it and prove it to yourself that everything that I'm telling you is in fact true. Okay? Well, I hope you've enjoyed this little presentation, and join me again in the next episode. Goodbye.